Uh, so the next speaker is actually it's an honor to have him here, and we have Dr. Witherell, and he's working at the National Institute of Standard and Technology under the U.S. Department of Commerce. He has tremendous amount of experiences on additive manufacturing, which is the a national focus right now for manufacturing, advanced manufacturing technology. And we are working with him right now, try to adopt artificial intelligence, data science. Those are terms a student may have heard of. You will wonder, hey, those are computer science. How do you do computer science in manufacturing? Actually, computer science, a big application of computer science is in advanced manufacturing. Now we move into the era of digital manufacturing, cyber manufacturing, and of course, it's going to be a critical part of advanced manufacturing. So I hope today we can learn from Dr. Witherell about what's going on in his lab, and especially about additive manufacturing. Paul, are you ready?
Yeah, thank you very much, Dr. Lee, for the introduction. Good morning, good afternoon, all. Yes, Dr. Lee covered a little bit about what I'm going to be talking about today. I see that we've already done a little bit of additive manufacturing, so I'll give you a brief introduction to 3D printing and additive manufacturing, some of the overviews and some of the applications before going into some of the work that we do here at NIST. And when we go into work, some of the work that we do here at NIST, I'll talk a little bit more about NIST as well. So with that, we'll go ahead and get started. So I think we've got this far already today. So additive manufacturing and 3D printing are terms that are also often used synonymously, very much referring to the same thing. I picked this slide and this definition because I think it's a nice starting point, where 3D printing is as simply as having the third dimension to printing. It's a phrase used to describe the process of creating three-dimensional objects from digital file using materials printer in a manner similar to printing images on paper, but with a third dimension. So what you see there is what you might see. It's some typical maybe at-home 3D printer in a little box, and something is creating a polymer part or a plastic part. And so that's really the basics. In additive manufacturing, again, and on the next slide, we'll talk about some of the different terms that are used to describe these types of processes. But this is maybe another a little more formal way of referring to 3D printing. With additive manufacturing, is a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to abstractive manufacturing technologies. Some people like to differentiate 3D printing from additive manufacturing in the sense that additive manufacturing is more of a production process, something that's used by manufacturers to create parts for people, where 3D printing is often thought as, sometimes we'll make the argument that 3D printing is more the informal type process. In reality, there's a lot of different names to refer to this idea of creating or manufacturing an object or geometry layer by layer. Some of the names that people will hear are 3D printing, layered manufacturing, freeform fabrication, direct part manufacturing, rapid prototyping. So these are all different iterations of some of the language that's been used over the years to describe what's going on. We're creating a part three-dimensionally using two-dimensional layer by layers, or sometimes called the 2.5D as well. The point here is additive manufacturing is an umbrella term used for a set of processes and technologies developed over the past 30+ years. So you notice in the previous slide too, where we're talking a little bit about the additive manufacturing definition. It came from a standards organization, ASTM F42 ISO TC 261. So that's a standards organization that I work with, and I'll talk a little bit more later on, but that's where we get some of those formalizations for what's going on with additive manufacturing and 3D printing. So in the gist of it, what makes additive manufacturing, 3D printing special from what's been done for a long time is very simplistic. And in this next couple of slides, where if you want to oversimplify it and call manufacturing, and there's a lot of different ways to differentiate types of manufacturing, to differentiate additive from subtractive, we can look at this. So if you wanted to make a sphere, you wanted to make some sort of globe, the really old way is you might take a block and you might take out a lot of the manually take out and remove a lot of material until you get the shape that you want. If you think of whittling something, if you're familiar with that term. The more modern way, what we see a lot with the manufacturing of large metal components is generating a 3D model, generating a CNC program, and then machining away the unwanted material. And so a lot of these components that are being developed in additive manufacturing, particularly in metals, and this is a metals way of doing something, in the past have been done with subtractive machining, where you start with a block of material, you start with a set of material, and then you remove the unwanted material until you get to the shape that you want. As I think we know by now, the additive manufacturing is different, is that we generate the 3D model still, but we use software to slice the three-dimensional model into two-dimensional slices, and then we build each of those two-dimensional slices layer by layer. And so that's in essence what we're referring to when we talk about 3D printing. And there's actually a lot of different ways that building can be done. Key advantages of additive manufacturing: we can do some very complex geometries that we can't do using other processes. We can create internal passageways. We can create shell volumes that maybe you can't create using other processes. You can engineer porosity, the idea of creating cavities within full parts to perhaps do lightweighting. Lattice structure is something that's often used in additive manufacturing, particularly when it comes to the manufacturing component and developing real parts. And that's the idea of creating these trusses like you see in this image over here and this image over here. We call those lattice structures, and here's what we call a unit cell. And so what you do is you can make this geometry and take this geometry and fill it in between here. And so what you do with that is you're taking advantage of solid mechanics. You're taking advantage of truss structures and how they dissipate loads, and you're removing the unnecessary material. So what you're doing is removing material, but still able to maintain most of the stiffness and really maintain a lot of the stress strain curves that you'll see from manufacturing. Functionally graded materials. This is something that's still being explored and still being introduced. They haven't seen a lot of that in production being developed in industry at this point, but that's the idea. We can start with one type of metal and finish with another type of metal, or start with one type of volume and finish with another type of volume. So one of the things that we could do perhaps with the lattice is transitioning from a lattice to a different size lattice, and that might we call a functionally graded material. Another thing that we might do is transition from a steel to aluminum. And so that's the idea, that you can shift the types of materials along a path, and the material behavior, the behavior of the individual materials will change the overall behavior of a larger part, of a macro size behavior of a larger part, of a larger geometry. We talked about the lightweight structural parts and embedded components, the idea that you can actually build the part in place. And so you can actually build two pieces to an assembly in place in additive manufacturing, and you can then make them have relative motion to each other. And so that's a unique trait to additive manufacturing, in that if you can account for the dimensional tolerances, that you can actually, and NASA's done it in creating a wrench where they have, I think, a 3-inch-pound wrench that they've developed with polymers, that they've shown that they can create a wrench in outer space that will do some very small jobs with plastic. But the idea was that they didn't have to create the two parts and put it together. They were able to create it all as one part. And by wrench, I mean the socket wrench. So I'll talk a little bit about some of the methods that are used in additive manufacturing. Additive manufacturing materials process. So I think we've heard a little bit on the bio side of things and a little bit of the applications. Some of the methods, it's actually a broad term, as I mentioned up front, and it's got a lot of different, it's increasingly becoming a broader term. Polymers, ceramics, metals, composites, papers, even cements now are becoming more and more common, where we see additive manufacturing and 3D printing of buildings where people are talking about it. A variety of material forms, filaments, resins, powders, sheets, rods, and as I mentioned with cement, slurries. We're seeing more the idea of using a filament and embedding fibers into filaments, and so delivering either a metal or a composite type structure using a plastic or a polymer and melting away the plastic, or using the plastic as a binder. And each of these different materials and forms, they all can be even differentiated yet again with the types of processes that are available. There's quite a few types of there's 7 types of processes, and there's many different processes. And so Next slide, we'll talk about the types of processes, but each of these processes will have different approaches. Some support different types of materials, different capabilities, and different purposes overall. So I mentioned the standards committee, ASTM F42 and TC 261. One of the things that we do in the standards committee is look to kind of describe these types of processes, come to a common understanding of what additive manufacturing and what these processes are. And so one of the things that they did in F42 early on, which is in the past 15 years now, was establish these are the types of processes that are included in additive manufacturing. Material jetting, binder jetting, directed energy deposition, material extrusion, vat photopolymerization, sheet lamination, and powder bed fusion. And in each of these types of processes, you can actually have individual processes. For powder bed fusion, sometimes you might use a laser, sometimes you might use an electron beam, sometimes it might be on metal, sometimes it might be on powders. Vat polymerization, sometimes you might use a laser, sometimes you might use a UV light ray, sometimes you might do it as a scan path, sometimes you might do it as a mask. So there's different ways of approaching these types of processes, different ways of creating the geometry. So I'm going to start with the top four to give you a little bit of a flavor. I think this is where most people are familiar with additive manufacturing or 3D printing, material extrusion, often referred to as the fused deposition modeling in the context of what's done in the MakerBot. And that was one of the early rapid prototyping, the Maker movement. The MakerBot was a big part of that just 5 or 6 years ago even. So the idea there is that it sort of works like a glue gun, where you can draw a filament and push it through a heated nozzle, and then what you do is you move that nozzle around within your two-dimensional area, and then once you finish carving out your layer, your two-dimensional area, then you move the base, and then you repeat that process. What you can do with the material extrusion is sometimes you can do multi-materials. Sometimes you'll have one material that's going to give you the actual structure and one material that's going to be used to be a temporary structure, where you can even wash away some of it now with a polymer. You can also do material extrusion with carbon fibers. You can do it with metal as well. And so as we advance in additive manufacturing, I'll talk a little bit more about the science in the second half of this. What we're able to do is we're able to improve our processes, but also improve our capabilities. Vat photopolymerization. So this is another one, and here I'm giving an example with stereolithography. Stereolithography is an additive manufacturing process which uses a vat of liquid that's UV curable. And what you do is you hit it with a UV laser to create the layer by layer. And so vat photopolymerization, that's, I think, where you'll see a lot of the things that in stereolithography is where you'll see a lot of the parts that are currently created by additive manufacturing. So this type of one, because it uses a liquid, you'll get a little bit resolution than you will with something like an FDM printer or a material fusion printer. Though those printers are giving you better and better resolution. So a lot of times when you see something, if you've run into something in a museum that say that they 3D printed this, or you see some small type shape that you realize that you know has been 3D printed, a lot of those times that's been with a vat polymerization. So these are fairly affordable type technologies or processes. They give you a little bit of resolution. The material extrusion one that I showed in the previous slide, that's probably what you mostly see when you talk about the maker movement and the idea of being able to 3D print at home. More often than not, those machines are being used to 3D print at home. And entry level for some of those is as low as $100 or $200 now. But even and that might require a little bit of do-it-yourself, but for a fully operational one that's commercially available, you might be able to get one for as low as $400 or $500 now. So that the price entry and entry point has really come down over the years, and to get into additive manufacturing and 3D printing. And these are two of the most common processes where people really start a process where people start to learn and get engaged with the 3D printing and additive manufacturing technology. So sheet lamination is a little bit different, and this is meant to introduce this one here to kind of give a little bit different types of flavor. And so in sheet lamination, which is still considered a type of additive manufacturing technology, you're not moving a laser, you're not moving the filament as you draw a path. What you're doing is you're literally laying it down layer by layer with a sheet material. And then you're carving out. You could use a laser to carve it out, but instead of depositing the material, you're depositing the layer all at once, and then you're carving around it. And so that's a little bit different, where you're using the raw material process that's created by the sheet metal, and you're using some sort of binder between the sheets that's going to allow you to create the three-dimensional part. And so whether it's an adhesive coated paper, I think more and more you're seeing some sort of some friction welding too between some of these sheets to kind of get them to bind together with a little more on the materials and the material side of things. But that's a little bit different flavor of the additive manufacturing processes. And finally, I want to talk to you about this one, powder bed fusion. Coming from NIST, this is where I spend a lot of my time. This is where a lot of our work is done. And I'll tell you as I move into applications to the next part, what powder bed fusion really offers. But powder bed fusion, it's either going to be with an electron beam or a laser. I'm most familiar with those that are done by a laser, where the melting is done by a laser, and it can be with a polymer or with a metal, and even ceramics is being explored right now. And so with the polymer, what you're doing is you're going to center the polymer, center the plastic bead, and what that does is start to create a binder, and so you form your part based on the material. When you're using a metal, you're not doing the centering. What you're doing is you're fully melting the metal powder. And so when we talk about powder bed fusion in additive manufacturing, particularly from my background, and I'll go into this in a lot more detail in the next second half, is we bring this metal powder to a full melt, and we study, and we by fully melting the metal powder with a melt pool, we're able to do the layer by layer and create fully dense materials. So this diagram on the right here shows how the powder bed fusion works, where you have the material is coming up on the left, and you've got the build volume or the build plate on the right. And so you'll introduce more material, you'll sweep it over, and then you'll melt that material, or you'll center that material to the solid geometry that you're trying to create. And then you'll move your build platform by a step of Z, and then you'll continue that process. And I'll actually show you later on this process at work. So what are the projected impacts of additive manufacturing? And again, this goes into somewhat into our everyday life, but very much into what we're able to do with industry, and what we're able to do in manufacturing, in the manufacturing industry. Rapid product transformation. This idea of print to part is not really there yet. Art to part is something that we're seeing very much of. And I'll talk about the applications in the next few slides, but the idea that you can create one-offs without a lot of preparation, without having to design a new manufacturing process for it, but by simply creating a computer-generated model, you're able to create a geometry without a lot of intermediate steps. And so when we're using something like a filament, and even more some of these metals processes, we're able to create geometries by really simplifying the processes that may have been used in the past. Improved performance with reduced weight. We've talked a little bit about that with the lattice structure, and the idea that we can take advantage of material characteristics, and we can use unit cells within a part volume, and we can start to remove the material while still maintaining an effective stiffness. The cost-effective personalized production. The idea that, we talked to, for those of you who have been involved in industry for some time, or have been exposed to a lot of different types of industry, from mass production to more of the mass customization type thing, where you can personalize things with additive manufacturing. I'll talk about that in the next couple slides when we look at the applications. On-demand fabrication, the idea of potentially getting what you want when you want. We're seeing this a little bit if you're able to go online and find somebody that you've got a design, you want somebody to create your design. In the past, there might have been a lot of setup, there might have been a lot of lead time into getting your design to somebody that was able to create it. More and more, you're even just able to go into a shop yourself. I know we have some, I'm from the DC area, Washington, DC. We have some maker spaces near us where I can go into a maker space with a model and actually create something that I want to create by myself. Or there's lots of people out there, more increasingly lots of people out there that I can go online and I can look at these shops that are able to deliver a part for me after I give them the model. And this is increasingly available, much more than it was in the past. and bringing manufacturing capabilities to remote locations. This is something that's particularly being explored by agencies like NASA and the military. The idea of not having to bring all your spare parts with you, but the capability to recreate your spare parts when you need them. So now I'll talk a little bit about some of the applications in additive manufacturing. So how is 3D printing changing the world? Medical, advances in research, prototyping, preservation, engineering, architectural engineering, advanced manufacturing, food industries, automotive, accessories. So this was, meant to just show you there's a lot of different places that additive manufacturing is touching, that 3D printing is touching. So now I'm going to go ahead and go into a little bit more concrete examples of some of these. Here, I just decided to label this trinkets, and this is the idea of, this is a lot of stuff that you might see as you make at home. When you're making something at home. I know for me, before COVID, when we would travel places and go to someplace with a gift shop, more and more, say you go to someplace like Paris, where they'll actually sell Eiffel Towers that have been 3D printed. And so the idea is that you're starting to see people make some of these trinkets and make these physical objects more available to the general public. Some little bird decorations see up there, little action figures. Even as simple as customizing your phone case is a fairly common application. And here, they have actually data repositories called like Thingiverse or GrabCAD, and those are places where you can go online and you can actually grab designs that other people have done and use them yourself. And so that's where you see a lot of neat things. And so you can, there's a lot of sharing that's allowed by 3D printing too, where particularly with Thingiverse, you can go on Thingiverse and you can grab, I've printed for like a runner, a statue of a runner from Thingiverse, and I'm able to customize it, maybe put it on a little platform, and then create it myself at home. So this is where you might run into very much in the everyday world, is the 3D printing side of things. Jewelry is another one that people are getting a little more, trying to take advantage of a little bit more, particularly what's going with what it was to do with the fancy jewelry and the not necessarily just costume jewelry, but jewelry that's artistic. The idea of designing something that can only be created in certain ways, and so that's something that you are starting to see more and more of, I believe, in jewelry stores. Food, this is something that's becoming more and more common. I know there was an article a couple of weeks ago where somebody had 3D printed a steak that was actually a very difficult steak texture to normally achieve, but they were able to do it with 3D printing. And here's a simple one where there's more of the, what you see is a chocolate, and the idea, again, the layer by layer where you can eat your face machine. And these are just ways where you can interact with 3D printing and some of the neat, novel capabilities that are being created with 3D printing. As we go more into the how do you improve the quality of living type of thing, prototyping. So 3D printing has really changed how people have done prototyping. In a similar way that modeling and simulation have. So we've really come to rely a lot on modeling and simulation to reduce the amount of actual physical prototyping and physical testing that needs to be done. But there's always something to be said for a physical observation. And the prototyping is one of the earliest practices of 3D printing. And the idea that we could, instead of trying to get the part just right from the model, we could actually print the model. And that's what you're seeing right there, where somebody's creating a race car, have to do some drag tests, some aerodynamic tests on how it performs in a wind tunnel, and be able to get that shape just right and create that complex shape directly from the model. We're seeing that in architecture. I think we're seeing more and more we can tour homes virtually, and we're integrating with the 3D environment and the idea that you can go around and take virtual tours of things. But there's always still something to be said when you get to see something physically and see what something's going to look like. And so architectures for some time now have taken advantage of, architects, I should say, have taken advantage of 3D printing technology to really realize their buildings, realize their communities, really show people and get that full wow effect of what some of these unique designs are look like when they're actually realized in the physical world. Dental is, again, one of the early applications of 3D printing. One of the machines that we have here at NIST was actually originally developed for dental applications. So the dental procedures in the past, there was a lot of work that needed to be done for the molding, that it would take quite some time before you could get back perhaps the tooth mold that would best work for a particular person. 3D printing really cut that time, I think, by a fraction. And so it became a much quicker turnaround for people who needed to do some of that dental stuff. And so it became much more accessible as well. So that was one of the early applications where 3D printing really had some success. And here, moving on from dental, is sort of bottom right. It's got teeth, but it's more of a prosthetic. And so, or medical, I should say. And so the medical applications, and this again goes to this idea of customization and being able to create parts that are of high quality, but with very specific details. And so right there you see a hip socket. And again, you see that lattice structure. What's kind of neat about this application is that with this hip socket gets inserted into a person, or somebody who's going to receive it, a patient, the lattice structure and that porosity there, that is, if you weren't using 3D printing, you wouldn't be able to create that structure. It actually facilitates bone growth. And so what it does is it helps, it improves the performance of your artificial hip socket, because by exposing that porosity, it supports the idea that your bone tissue can grow it more naturally. So previously, you would have seen holes drilled into something that was completely solid, but by introducing this more porous structure, you actually have a higher success rate in their implementation. You see some more mechanical parts on the top right, and even hearing aids, and the idea that creating a hearing aid, every person's ears are different. Why are we treating them all the same? And how do you kind of customize for a particular application and for a particular person? Prosthetics, and so I mentioned that I would talk about this again. So we saw that jaw earlier on, the dental one, and here we're seeing the idea that, every body too has this particular weight balance, and so the idea of how the weight distributed and how somebody interacts with an artificial prosthetic. Some artificial prosthetics can be very difficult to fine tune and to get just right. 3D printing not only helps you with iterating through those processes and getting kind of finding where that fit works out sooner, but it also helps you create some better, if you would, some better distributed, some more advanced prosthetic technologies, prosthetic parts. Here on the right is a bald eagle, and so on the left you simply see a woman who got an artificial leg. Perhaps I'm not sure if her foot is 3D printed as well, but I'd imagine it is. And so you're not only seeing the metal part of the leg, but the silicone that could be, and the detail that can be added for the foot. On the right, what you're seeing here is you're seeing a bald eagle, and this bald eagle, it's unable to survive without the full beak because it needs to eat. And so what 3D printing allowed to do, additive manufacturing allowed to do, was create a fast, quick, meaningful solution that bald eagle was able to receive, like customized wood beak, but also something that somebody could just do it on the spot. It wasn't something where it was a 2-week turnaround. It was something that was probably a 2-day turnaround, where the beak was generated and then it was manufactured. And so this eagle was now able to eat on his own, be sent out, and live in the wild. And finally, for last, I saved advanced manufacturing, aerospace, automotive, and defense. And this is where I'm going to live for the next few minutes, is talking about what NIST does and a lot of the work that we do in this area, particularly with where I'm from is in the metal side of things, in the measurement science for additive manufacturing lab. And some of the applications that, not necessarily applications, but some of the research that we're doing to help the application, those the people that are using these applications, but the aerospace, defense industry, medical industries should be in here too, but for the advanced manufacturing of parts. So additive manufacturing at the National Institute of Standards Technology. So NIST is a national lab under the Department of Commerce. Our mission is to support U.S. commerce through measurement science. When we talk about measurement science, what we do is we're talking about the idea that there's quantities, there's things that can be observed and that can be measured. And by making observations and measurements, it allows us to make better decisions. It allows us to improve things. And so what NIST does and what we do is we look at what can be observed, what can be measured, and how are things improved. We actually have a very broad area of application of where our research. We have our main labs are the physical measurements lab. They're fairly famous for operating the atomic clock. And that's the idea that we can measure time and we can keep track of time. And we actually keep track of time for all of the US in Boulder, Colorado. We have our materials measurements lab. They've done quite a bit of work with Materials Genome Initiative. And that's the idea that we can break down materials into things that can be designed. We have our communications technology lab, which played a large role in the transition from 4G to 5G for our cell phones and understanding the wireless spectrums and the implications of changing those frequencies. And we have the Information Technologies Lab, which is very well known for the work they've done in cybersecurity and also artificial intelligence. We come out with guidance on cybersecurity. We also come out with, we do quite a bit of work in understanding bias in artificial intelligence and fundamentals of artificial intelligence. And then we have the engineering lab, which is where I'm from. We used to be separated as a building and fire research lab and the manufacturing engineering lab. We were joined with the engineering lab. And we've done a lot of work as well. We were responsible for investigating what actually caused the failure of the World Trade Center and what caused the buildings to finally fall. If you're familiar with the building collapse in Florida over the past couple of months, and this actually sent a team down there to investigate where the building codes failed and why those buildings fell. We've done quite a bit of work in the manufacturing area as well. I come from the Systems Integration Division. My colleagues in the program also come from the Intelligent Systems Division. We do work in robotics. We do work in manufacturing. We do work in larger systems engineering. And yeah, I guess that's pretty much covers our manufacturing spectrum and our intelligent systems spectrum. And so that's where I'm coming from. And I'll talk a little bit of work now about our measurement science for additive manufacturing program. So additive manufacturing at NIST is actually something that is not specific to the engineering lab. We actually have it across labs. We have collaborations across labs. I'm going to tell you a little bit about some of the polymer work that's done in materials lab, and then some of the work that we do in our measurement science for additive manufacturing program. So NIST and additive manufacturing, as I mentioned, it's really a cross-lab effort. We develop the measurement science, and manufacturers and technology providers use NIST test methods, measurement tools, performance measures, and scientific data every day. We're very involved in standards development. So one of the things that we do outside of measurement science is we use that measurement science to come to basic understandings. You know, I mentioned the atomic clock, but we also more recently working on the redefinition of the kilogram and the idea of taking the definition of the kilogram from an actual physical quantity to something that can be reproduced using atoms and moles. And so NIST played a large part of that in the past couple of years. And so, you know, what are our measurement standards, our time standards? NIST really does the fundamentals that addresses many of those things. And we're not addressing it at the fundamental science level. A lot of times we're addressing things at the applied level. And that's where we start to see interactions with standards communities, whether it's ASTM standards communities, whether it's ASME standards communities, whether it's the International Standards Organization communities. And so we do a lot of standards development work there and partnerships. Working for the Department of Commerce, we work with a lot of academic folks, and we work with a lot of government folks, and we work with a lot of industry folks. What we really focus on is measurements and standards. So additive manufacturing with polymers, we talked a little bit about this already, and the idea of material extrusion, fused deposition modeling, and how that works. But now we'll look a little bit more into the science and how that layer by layer happens. And what we're seeing there's a weld zone. So when you deposit one layer on top of another layer, what is the observation that we're actually making. And so here you're seeing the fused deposition modeling, again, in the polymer interaction and that layer by layer interaction. And so some of the stuff that we do here in NIST, and this is coming out of our materials measurements lab, is looking at this layer by layer interaction and actually sticking a thermal camera on there to make observations about what that interaction looks like, to understand what's happening, what is the science of happening. And what we're enabling ourselves to do is to look at the heat, look at the temperature, and analyze how that filament is being deposited, and then study what the interactions between the layers are. So here you can see, this is a snapshot, but this quick video right here, you can see what you're doing is we're looking and we're taking video of, this is a thermal imaging of what's going on the megabus. So you can see where it's hottest, and you can start to see the cooling patterns too of the filament on the path by path, layer by layer basis. And so that's an example of some of the work our materials measurements lab has done to studying the polymers. Coming from the engineering lab, our focus when we created the Measurement Science for Additive Manufacturing program was to really focus on metals additive manufacturing, and that's where we have been for the past 8 years of our program, to really focus on supporting U.S. industry and those I guess those industries like aerospace, biomedical, dental, and automotive that are really leveraging the technologies to develop one-of-a-kind parts that couldn't be developed otherwise, and are really taking advantage of the additive manufacturing processes to do very critical applications. And so here we see a heat exchanger, we see a plate in the human skull, we see the light weighting, and this is the LEAP fuel nozzle, and here we see a turbine blade. And so the idea here is the additive manufacturing is actually being used to create parts that have been created somewhat in other ways, but here we're seeing where it's created better. Here we're seeing where it's created better. Here there was a part reduction of quite a bit. We're created quite a cost savings. And here we're seeing some very unique geometry. So I mentioned that I'd show you an actual example of the powder bed fusion. And so in our lab, we actually have three powder bed fusion machines for metals powder bed fusion, all with laser. And so right here, we're watching the laser powder bed fusion process of metals. We have one binder jetting machine, and we have one directed energy deposition machine. But a lot of our work in our first machine was on the powder bed fusion machine, and a lot of our work has really continued on the powder bed fusion machine. So here is an example of what's actually going on in the process when we're creating something. So the laser is melting it, and then we're going to see another layer of powder come across, and then that process is going to repeat. So where does NIST come in? As I mentioned, we do measurements. We look for things that we can measure so we can start to improve the process. And so what we found is metals additive manufacturing. It's been a maturing technology for almost 40 years now. But it has matured. I don't have the history of additive manufacturing, but it's matured from a state where it was very sloppy to start. It was essentially just welding layer on layer on top of layer, at the point where you could get a rough outline of a shape or of a geometry, but it wasn't necessarily something that you're going to put in a car or put in an airplane. But we are doing that now. So how do we get from something that doesn't really look like we want it to something that we're now putting in airplanes and that we're now putting in cars? And we're doing that by better understanding the process and better understanding the constituents of the process, and better understanding how to evaluate the part after the process, after it's been completed and fabricated in the process. And so that's where a lot of our work at NIST, all of our work at NIST is focused on, is better understanding the raw material, characterization of the raw material, measuring the raw material, better understanding the process and measuring the process, and better finding new ways to measure the final part, to build confidence in the final part. And so that's where most of our projects really lied. And there's actually a lot of uncertainty quantification. As a digital process, there's a lot of data that goes along with that as well. And so Dr. Lee mentioned, the role of AI and machine learning techniques. And a big part of how we learn from these things is we sense a lot of data, and then how do we analyze the data to make new observations and reach new conclusions. So here's some of the observations that we're making on the material side of things. On the left, you're seeing the powder rheology, you're seeing the powder flow. And this is what it does, is it helps us, we make the observations, we're able to do the simulations, and then we're able to do the studies as well, simulations of this flow, and then put it into the operating environment. And what we're doing is trying to understand how do we achieve a specific type of density. So when we're using the laser to melt the powder bed, how do we distribute the powder in a way that we're going to get the fully dense product that we want? And so we're actually able to measure the behavior of the powder, simulate the behavior of the powder, and then observe and make predictions about how that powder is going to behave. And then we can repeat that. Measuring the process. This one is something where I mentioned in the powder bed fusion, we're using a laser and we're going over a powder bed with the laser, but in solidifying a part one path at a time. And so this is a part that was fabricated in our in-house built powder bed fusion machine, which I will show you that. And what you're seeing here is you're seeing a thermal imaging, similar to the polymer, but this is for the metals. And so this is a thermal imaging camera. And what it's doing right here is that's the laser that's tracing over this path right here. So this is this part being created with a laser. And so what you're seeing here is you're seeing what are the this is actually a reflection of this is actually measuring the heat at the melt pools with the thermal camera. And so what this is doing here too is you're seeing the heat from the spattering. And so that spattering right there, that creates some variances, some variety in the final part quality, because, and that goes right back into the powder and how the powder was laid, but depending on how the laser interacts with the powder, you can create powder spattering, and that powder spatter will actually change your surface finish and actually change your final part qualities. We can look at things at what the microstructure looks like after the part's been melted, after the metal has been melted, and after the metal goes through different solidification phase, what type of microstructure is formed and what is the behavior of those microstructures, which we'll go into the qualification aspect of things. But when we study the process, one of the things that we're doing is looking at, what are the ways that we can improve the process. And so here, this is actually our in-house machine, the Additive Manufacturing Metrology Test Bed. And so this is a powder bed fusion machine that's one of a kind that was built at NIST, with the key phrase being metrology test bed. And so this machine was built with the idea that we can measure and we can observe and we can measure things and we can change our measurements. We can change our measurement technology. We can change our technology because it's our machine. We also have organic control over the scan strategy. That's something that's not normally seen by a lot of these commercially available machines. So I guess I mentioned earlier, when it gets to powder bed fusion, a lot of the commercial machines, so the powder bed fusion is a common technology that's being used when we're using the aerospace applications, the medical applications, and the defense applications. And those machines, entry level, normally around $600,000. So I mentioned the polymers early on, you can get for around a few $100s. These machines are very much cost prohibitive. And so when you do purchase them, it's for commercial use, and you want to have good, and you expect good part quality out of them. And because of that, a lot of these machines, what they'll do is they'll work very hard to make their machine work as they're able to design it with what they can control. What people want to do is they want to be able to have some control too as well. And so there's a natural conflict there where the more the manufacturer opens up the machine, the less they can guarantee the quality of the part that's being created. But the person, the user ideally wants to open up the part of the machine so they can have some more choices into how the different parts are developed and have some more variety in how they approach things. And so it creates a little bit of conflict with some of these commercial machines. And so by having an in-house built machine, we're able to have full control over everything that's going on in the machine in our entire build process. And what that does here is you're seeing how we're able to control the scan strategy, which is something that's usually built into the commercial machines, but in ours, we have full organic control over it. And again, going finally into the qualification part of things, we talked about the material, we talked about understanding and improving the process, and how do we know that our part is good? And so NIST is doing a lot of work using X-ray CT, XCT, using optical surface measurements as well, and studying what are the qualities of the final part. So here you'll see an image is a 3D image here of an XCT reconstruction. And so this, what you're seeing here is an example of how you might have keyhole porosity. So you have full density and only partial density. And so what happens with powder bed fusion, if you don't get a full melt, or if you move the laser too fast or heat up the laser too much, you might not get a fully dense part. How do you know that happened? And so one of the things that you do is you can use something called X-ray CT, similar to what we use when we get an X-ray if we have a broken bone. And we can use that same technology to actually investigate how well we're able to create our parts. So finally, I'm going to end up with, what are the facilities that we have at NIST? We have our Additive Manufacturing Research Center that you see right here. So we have our production machine, the EOS M290, which is where we would create a lot of our parts that are meant to be on par with what industry sees. We have a directed energy depth machine. We have our binder jetting back here. And we have another EOS M270 that's not in this picture. So we have our production center, if you will. We're able to do a lot of creative parts and do a lot of our measurements. We also have a lot of measurements that are specific to depending on what we're doing. Here is one of our machines that allows us to measure powder size distribution. And so this allows us to measure the powder itself. This is a machine that's allowing us to measure the surface characteristics of the parts that are made. And this is a machine that allows us to calibrate our laser in that machine that I just showed you, which is a different lab that we have, the Additive Manufacturing Metrology Test Bed, the TIMS laboratory. And so here we have our fully open machine that was developed in-house. We're able to control the process completely by ourselves and also set up our own measurements for the process, so we can really start to understand the process and measurement itself. And we actually, when we set this up, we worked with our physical measurements lab to the point that we created a unique, one-of-a-kind way of measuring the true temperature of a part and the emissivity of a part. And so and I didn't talk much about the modeling aspects of things, but the true temperature really improves your understanding of the process itself. And people were using temperatures that were taken from different processes that weren't specific to additive manufacturing. What we did working with our physical measurements lab was develop a unique temps lab that we call it, that allows us to get calibration of temperatures to something that hadn't been done before. So that was something that was unique that we've done in this, and really took advantage of our measurement and capabilities and some of the work that we do here, some of our expertise. And of course, the standards aspects of things. And here you'll see some witness coupons where NIST is involved in working with entities like ASME, ASTM, SAE, ISO, AWS, in developing standards that can be adopted by industry to help have a more consistent interpretation of the material, of the process, and of the final part. And so here's an example of some of our engagements. Again, ASTM, ISO, ASME, SAE, AWS, and ANSI. And here's an example of some of the standards we've worked on with the standards test artifact, product definition, GD&T standards, the characteristic of surface technology. If you do get involved in the future of ASTM standards, more likely than not, you will be involved with somebody who's very much engaged in this program here at NIST. So with that, I thank you for your time and thank you for listening. I think I still might have gone a couple minutes over. And so here's a couple of pictures of us from being engaged at the Maker Fair and Capitol Hill Maker Fair and the National Maker Fair here in Washington, D.C.
That's a great presentation, Paul. Yeah, before I think we can collect questions now, but then before you answer a question from students, let me just add some comments and questions I have. And you mentioned about custom-made system. I read that article. Were you a part of that effort? Somebody your colleague?
No, so that was myself personally. No, that wasn't done in my project. So in our first iteration of the program, we first created a measurement science for additive manufacturing program in 2013. We had 4 projects in that program. I led the systems integration for additive manufacturing project, which was focused on the data and data science associated with additive manufacturing. My colleagues led the materials project, the qualification project, and the process project. And so as part of the process project, one of the things that we really wanted to do was create a new platform where we could do some of those very difficult measurements that we weren't able to do with the commercial machines. And so that machine was developed under our process project, but with contributions first set forth with some early interactions with EWI and a grant that we had given them. We worked with some colleagues from South Africa. We work with colleagues from Canada, from Europe as well, in developing the final design for that machine. But it was very much about 3 to 4 years in the making before we put that together.
Yeah, we actually, as you mentioned earlier, at UTRGV, we have 2 metal machines now. One is Renshaw AM250, who acquired back then in 2014. So it's about 7 years old now. So we are acquiring a EOS AM290. So that machine we're gonna use in the NIST project we're working together on. And then we are also trying to set up a new customized system for materials under extreme conditions. So we're trying to investigate high power laser available in the industry now. But I would like to know if we can work together on that, especially the system, the custom system you demonstrated. Hopefully we can send some of our students to work with you over there if it's possible. But
yeah, sure. We've actually developed a second custom system since. This system was developed for the chest laboratory at Cornell, and what they're able to do is they have an X-ray synchrotron, and so what we're able to do there is study the process itself using X-ray sources during the process, so not after the process. And so we had worked with those folks, and we developed our second machine, and so that it hasn't been deployed yet because of the COVID restrictions, but it is something that we have completed development on. We've also worked with NASA, NASA Langley, and their research center. They have an open source custom built machine. We did some iterations there. And we also did some work with Auburn. The University of Auburn University had sent over some students to try to learn a little bit of. Actually, Auburn University was supposed to send over a student, and they didn't end up finally sending them over. But they were also looking for a custom built machine as well. So we have done some of those interactions in the past, and we'll be open to that in the future.
Yeah, we're gonna follow up on this. I think we got some questions here, and
3D printed houses cars reliable. 3D printed cars reliable. I think a lot of those 3D printed cars you see, particularly one that came from Oak Ridge, there's some smoke and mirrors in there. So they'll 3D print the shape, but that really large piece is not something that was done fully 3D printing without a lot of post processing. With that said, there is a company called Locomotives who is creating 3D printed cars. So there are companies that are being developed to make sure that reliability is going to be there. I laugh because it makes me think of somebody. I remember reading this article maybe a year ago, where somebody had created like a Lamborghini Countach or something like that, and it was from like an old Ford, and they actually 3D printed the entire outside of the car to make it look like a Lamborghini. And so in that sense, you've still got your traditional car, and then you've got the parts to make it look like, but I wouldn't necessarily have been driving around that car, and I probably wasn't that safe. But they are creating 3D printed cars. They are putting 3D printed components into our cars. Formula One is very much putting some very high-end 3D printed components into their cars to improve their performance. The houses, that is work that we are doing inactively. Are not in a Measure for Science for Additive Manufacturing project, but we're focused on the manufacturing industry. But for the building industry, we definitely we have folks here that are working on, and we actually had a workshop I want to say about a year ago about using cement and 3D printing. It is fairly reliable. They're able to, if you're sticking with cement, sticking with a slurry, it's a neat way of laying down the parts of your house, and it's not too different from regular cement. So a lot of the 3D printing part is getting the slurry just right, where you're able to get it to solidify in the right manner, while at the same time being able to keep that viscosity and that flow rate good enough that it's continuously building. But we are seeing more and more successfully printed 3D homes. Again, it doesn't mean the sink was 3D printed and all these other things were 3D printed. When they had 3D printed home, they printed a shell, and those are very much a reality that can be done now. I think we're still working to justify what the advantages over something like that are. I think a lot of times the case people are trying to make is there's a cost advantage there, but I'm not, it's only a cost advantage if you're doing them in large quantities in a small area, and so I'm not sure that's always the case.
Well, let me add a little bit, Paul. I know a few commercial company at Austin. They have commercialized their idea of 3D printing for houses. So that I think is pretty successful now. I don't have the link, but if any student interested, I'll share with the teachers a link about those companies. And we worked with NSAN last year, the National Security Innovation Units, and it's under DoD, and they have commercialized or incubated a few companies working on 3D printing for houses. So
okay, thank you.
Yeah, it's in Austin. If you want to go, even I can connect you with those companies.
Yeah, the one that does the cars is actually in Virginia, so it's not too far from me. And we actually did do a trip there a couple of years ago. That's a great question as far as this high school college students to work at NIST. We have something called the SHIP program and the SURF program. And I would encourage you to look at and engage with both of them. We support national participation. We provide housing in the SURF program. We provide, I believe we do travel as well, and it's fairly competitive. It's a fairly competitive process, but it is a great opportunity. What you'll see is there'll be people in our program and our labs that will put out projects, and so it becomes a little bit on part of on our side to put together a project and put something out there where somebody can then be selected for particular projects. And so it's a matching process between NIST and the students. And so the more projects that we're able to come up with here at NIST, the more students that we need to support our projects. It's very much an onus on the researcher here at NIST to make sure that we're creating projects and working with the students so that they're getting a good learning experience. But we've had some very successful experiences out of this. If you'd like to follow up on that, I'd encourage you to reach out to Dr. Lee, and we can see what opportunities there are there. It will close sometime in February for the SURF program. And I am talking right now, but if I will put that in the chat as soon as I'm not talking, so you can see that link and learn more about it.
Yeah, add another comment here. If you're interested working on either with NIST or with any other national agency, including DoD, including Oak Ridge National Lab, on these topics, you come to UTRGV Manufacturing Engineering Department first and become a college student. Then we're gonna open up all these opportunities for you. Right? Yeah, you can work with me first. We're going to prepare, just like Leslie and some other students presented today. They are supported by the consortium working on these projects, right? So we can send you over to the different federal agency and work in their lab. So that's the way we try to provide you a roadmap you can follow. So you get ready when you have this opportunity, showing up, and you're ready to apply, and we connect you to the right person to talk to and to work with. And so that's why we have this consortium here, and just to help students to be aware and also to be ready for the opportunities across the nation. All right. Any other questions?
Well, thank you very much for your time, and thank you very much for having me. And I hope you all learned a little bit about additive manufacturing, and hopefully it generated a little bit of interest into what we do here at NIST.
Thank you, Paul. I really appreciate your time and effort, and I believe the students learn a lot. And even though they're not allowed to talk, but hopefully next time we can have face-to-face meetings, and we have the student right in front of you. That's gonna make you a little bit more energetic when you have the student, directly talking to you.
Okay, thank you again.
Thank you.